Alright, in this video I'm going to introduce type 2 error, and I'm going to stick with situations where the population SD is known, so we'll only have the Z distribution in this video. So at the end of every hypothesis test, you are forced to make a decision, either reject or don't reject the null hypothesis. This decision is based on probability laws that we talked about in previous videos, but it doesn't change the fact that each hypothesis test ends with some kind of declaration. So there are two possible outcomes for your decision: reject or don't reject. On top of that, the null hypothesis could be true or false. So there are four possible outcomes, as you can see from this simple table. Two of the outcomes represent correct decisions. If the null hypothesis is actually true, then not rejecting it would be the correct decision, and if the null hypothesis is actually false, then rejecting it would be the correct decision. But the other two outcomes represent mistakes, and they have their own names. If the null hypothesis is really true, but you decide to reject it anyway, then this is called type 1 error. Conversely, if the null hypothesis is really false, but you decide not to reject it, then this is called type 2 error. Another way of saying that is that you should have rejected, but you didn't. Before going on, I want to stress that we never know at any point before, during, or after the hypothesis test whether the null hypothesis is true or false. For example, if you decide to reject the null hypothesis, then it does not necessarily mean that it is false. You'll have made the decision to reject based on probabilities that assure you that you're probably right, but you'll never truly know for sure. So talking about type 1 and type 2 error means we have to ask what if questions all the time. What if the null hypothesis is actually true, etc. And I also want to point out that we also have some experience with type 1 error. This kind of error is closely tied into the framework of hypothesis testing. Remember that when we did questions about critical values and p-values, we always began by assuming the null hypothesis was true. Therefore, type 1 error was the only possible kind of mistake we could make. Furthermore, type 1 error is closely linked with the concept of level. In fact, level is defined as the maximum allowed probability for a type 1 error. So if I say that a test has 5% level, then I'm also saying that I'm allowing up to 5% probability of type 1 error. So you can see why we like to use small numbers for level. Most people don't use 10% level because that allows for a 10% probability that they will make a mistake, and that's just too high for most people. Okay, type 2 error questions look like this. You're given a hypothesis and a what if statement like this. But we're not going to deal with that until later. We're going to begin just like a critical value question because it's very important to determine where the threshold for rejection is. So our hypothesis is one-tailed, right-tailed, and here is the distribution, assuming that the mean is equal to 1200. Since the level is given as 5%, there is a critical value, k, such that the area in the right tail beyond k is 0.05. For the z distribution, we know that this happens when z is equal to 1.645. So we create z by subtracting the mean and dividing by the SD, and then we're going to set it equal to 1.645. Solving for k, we get 1234.9. Remember that if x bar is greater than this critical value, then we'll decide to reject, and if x bar is less than this number, then we'll decide to not reject. And this is what we're interested in because type 2 error is all about not rejecting. So the probability of type 2 error is the probability that x bar is below the critical value. But now we're going to use the mean given in the what if statement in the question. That's the other part of type 2 error, assuming that the null hypothesis is not true. So when we create z by subtracting the mean, we're going to use the number from the what if statement. Then divide by the SD, and we see that z is less than negative 0.71. Checking the z table, we see that this probability is 0.2398. And this is the probability of type 2 error if the mean is actually 1,250. Now we're going to do the same question, but we're going to make one change. We're going to use 1% level instead of 5% level. Before we go on, I'm going to share a bit of intuition about the answer. It's going to be larger than before. This is because type 1 error and type 2 error are inversely related. If the probability of type 1 error goes down, like in this question, then the probability of type 2 error must do the opposite and go up. Here is what the previous question looked like at the beginning. By changing from 5% to 1% level, you can see that the critical value is going to be further out in the right tail. Specifically, for the z distribution, we know that the area in the right tail is 0.01, then z is equal to 2.326. Again, we create z by subtracting the mean and dividing the SD, and set it equal to 2.326. Solving for the critical value, we now get 1,249.3. Remember that not rejecting means that x bar is less than the critical value. And we are going to do this under the assumption that the mean is actually equal to 1,250. Create z by subtracting the mean and dividing by the SD, and we get z less than negative 0.03. Checking the z table, we see that this probability is 0.488. So this is the probability of type 2 error if the test is at 1% level. Okay, we've seen this hypothesis before. It's the mean age of people at a bar. And here is the what if statement that tells me that this is a type 2 error question. Once again, we begin by finding the critical values. This is a two-tailed hypothesis, so there is a upper and lower critical value. Since the level is given as 5%, that means the area in each tail must be 0.025. For the z distribution, we know that this happens when z is equal to plus or minus 1.96. So here are my critical value equations. We create z by subtracting the mean from the null hypothesis and dividing by the SD. For the lower critical value, we set it equal to negative 1.96. For the upper critical value, we set it equal to positive 1.96. So our critical values are 26.19 and 27.181. Remember that we reject if x bar is greater than the upper critical value or less than the lower critical value. We do not reject if x bar is between these numbers. And that's what we're interested in for type 2 error. So we need to find the probability that x bar is between the critical values. But we're going to now assume that the mean is equal to 25, since this is the number that was given in the what if statement in the question. So we create z by subtracting the mean, 25, and dividing by the SD. We get z between 2.88 and 6.8. We can ignore the 6.8 since it's way off the z table. The areas out there are essentially 0. So we go to the z table and see that the probability is only 0.002. So there's a very small chance of type 2 error if the mean is really 25. Okay, this last question is another hypothesis that we've seen before, mean phone charging time. And here is the what if statement that tells me this is a type 2 error question. But this one is different. This time you're given the probability of type 2 error and you have to solve for the sample size. Well, it doesn't make any difference to how we begin the problem. We still need to find the critical value. Here is the distribution assuming that the mean is equal to 30. The hypothesis is one-tailed left tail, so the critical value k is in the left tail. Since the level is given as 5% area, the area beyond the critical value is 0.05. For the z distribution, we know this happens when z is equal to negative 1.645. Create z by subtracting the mean from the null hypothesis and dividing by the SD and set it equal to negative 1.645. Solving for k, we get this expression. It doesn't have a closed solution since we don't know n yet, but that's okay. We'll just set this aside for now and come back to it later. Let's just think about rejection. Since this is a left-tailed hypothesis, we reject if x bar is less than k, and we do not reject if x bar is greater than k. And that's what we're interested in for type 2 error. But now we're going to assume that the mean is 28, since that was the number given in the what if statement. Now we're going to create z by subtracting the mean, 28, and dividing by the SD. Now we're here. We were given in the question that the probability of type 2 error is equal to 0.1. Well, if z is bigger than some number with probability 0.1, then the area in the right tail must be 0.1, which means that z must be equal to 1.282. So set the z formula equal to 1.282 and we get this. I still don't have a closed solution yet, but I now have two equations involving k and n. Now, this is the point where I'm going to use the equation that I left aside in the previous slide. You might want to rewind and take a look at it. That equation told me what k is equal to, and I'm going to substitute it into this equation to get this beast. So this part here is what I substituted in for k. Now all I have to do is solve for n. It's not really as hard as it looks. After you multiply the denominator over to the other side, you can multiply through by root n. Eventually you see that n is equal to 90.49, round up to 91. Okay, that's a tough question. If you can handle that, then you can probably handle anything that I throw at you on the exam. Now you have 3 questions to try on your own. Good luck with that, and check out the next video.